In section 5.3, we're going to see what happens when we run out of one reactant before another. These are called limiting reactant or limiting reagent problems. We'll discover how to identify this type of problem and how to calculate the amounts of products and reactants remaining when one reactant is in short supply. Let's begin. So far, all calculations have assumed the reactants are present in the amounts needed such that no reactant remains at the end. This is not always the case. When one reactant is used up before the other, this reactant limits the amount of any other reactant that can react and how much product can be produced. For this reason, the reactant present in insufficient quantities for the others to react completely is called the limiting reactant. Other reactants left over are present in excess, and the reaction is said to go to completion when the limiting reactant has been used up. Let's look at an example. Suppose we have N2 gas, the blue spheres, mixed with H2 gas, the white spheres. Checking the balanced chemical equation, we see that one nitrogen molecule will react with 3 hydrogen molecules to produce 2 molecules of ammonia gas. If we do this for a second molecule of nitrogen, we see that when the limiting reactant, hydrogen, is all used up, we have nitrogen gas remaining in excess once the reaction has gone to completion. We can also say that of the 4 molecules of nitrogen initially present, 2 are in excess by taking the amount left over and subtracting it from the initial amount. Let's try this concept with a more relevant example. Let's discuss this critical scenario. A chemist walks into a coffee shop with $108 budgeted to buy coffee. The coffee beans are on sale for $8 per pound, but only 12.5 pounds are left in stock. How many pounds of coffee beans can the chemist buy? It's tempting to blurt out the back of the envelope answer here. The chemist can purchase 13.5 pounds of coffee. However, there are only 12.5 pounds in stock. So the correct answer is 12.5 pounds. You can't buy coffee that isn't in the store. Do you see how the amount of coffee beans was the limiting reactant rather than the amount of money? Our first step in solving any stoichiometry problem with a limiting reactant depends on identification of the reactant that will limit the amount of product formed. My preferred method is to calculate the amount of product formed from each reactant. Whichever reactant produces the least amount of product is the limiting reactant. For example, given 1.5 moles of methanol and 0.5 moles of oxygen, which is the limiting reactant? If we calculate how much product each reactant can form while assuming the other is in excess, we quickly see that oxygen is the limiting reactant because the amount we're given only produces 0.333 moles of product. Another way to identify the limiting reactant is to divide the moles of each reactant by its coefficient. The smallest resulting ratio is the limiting reactant. Let's see how that compares to the first method. With the second method, you can identify the limiting reactant quickly. Moles of methanol divided by the coefficient 2 gives us 0.75, while 0.5 moles divided by 3 gives us 0.167. The lower ratio tells us oxygen is the limiting reactant. Finally, I'll mention the third method because the book presents it, but this is usually more work than it's worth unless you're specifically trying to discover how much more you need of another reactant. Also keep in mind that reacting ratios are in terms of moles, not masses. If you're given a quantity in grams, you'll need to use the molar masses of all reactants to determine the limiting reactant. Let's practice. Using our previous example, let's calculate the number of moles of reactants and products that are present after the reaction is complete. The easiest way to keep track of everything is to add it to a table, which I've constructed here. I've noted the initial amounts in moles. We'll add the change of moles due to the reaction, then the final amounts after the reaction goes to completion. Since nothing is said about the amount of products, we'll assume they are both zero. From our previous examples, we already know that O2 is the limiting reactant. So it will be all used up, and that 0.333 moles of CO2 are produced. We can finish out this problem by calculating the moles of methanol reacted and the amount of water formed. Once we subtract the changes from the reaction from the reactant side and add them to the product side, we get our final amounts. Here's another example. Always verify first that the equation is balanced. Add your initial amounts to the table, then determine the limiting reactant. Let's do that by calculating how much phosphoric acid is produced. We see that PCl5 is the limiting reactant and 0.25 moles phosphoric acid is formed. Using that information, fill in the rest of the table. Here's a final example to work through. What mass of sodium sulfate will be formed by the addition of 14.4 grams of sodium bicarbonate to a solution containing 4.9 grams of sulfuric acid? First, verify the reaction is balanced. Calculate the number of moles of each reactant and product initially present. Determine the limiting reactant. Determine how much of the product in question is formed in terms of mass. If you'd like or need additional practice, consider working through the interactive in Figure 5.5 from the textbook. As always, I'll leave you with the parting thoughts of the authors. Don't forget to let the video finish playing through so that your scores will transfer to Canvas.